Hi, we are Group 16. Welcome to our IE413 and CS482 final project. Our group is aiming to utilize analytical simulation software Sigma based on the simulation techniques learned in a course to model a real-life system, a small-scale multi-server queue system in a hospital located in a small town. The objective of the simulation is to find out how many patients are waiting in a queue each day and whether the hospital needs to add more offices for treating patients. Since we have a group member who has worked for hospital system during summer vacation, this project is able to utilize the real-life data provided by the administrative staff of the hospital. The hospital is a Class B public hospital located in a small town with a population of less than 10,000 people. Doctors in the hospital are divided into 4 categories: specialist, regular doctor, first aid personnel, and assistant doctor, and also 3 types of patients: special patients and regular patients with no limitation buffer size in the queue, and emergency patients with a limited space of 1. Since Sigma has a limitation on the number of variables implemented, we simplify the model in order to simulate the system using Sigma.
For our assumptions, we have laws and policy. For laws, firstly, we have the transition times between different events are instantaneous. Secondly, all patients leave the hospital immediately after the treatment. And next, the inter-arrival time of patients follows an exponential distribution with mean lambda. And lastly, each patient sees 1 doctor, and all doctors present at the hospital on time and only leave hospital after working hours. For the policy, as you can see, we have 17 policies, and that's why we made this stop-motion video in order to show our policies. Our first type of doctor is specialist doctor, who will offer specialist sessions for patients. The second type of doctor is our normal case doctor. You can always walk in and wait in line for him. However, if that doctor is occupied, the next patients will be directed to our assistant doctor. We also have emergency type of doctor, who will only be able to treat patients with emergency need. At time of 8 o'clock in the morning, our hospital opens. The specialist type of patients arrive with probability of 0.3. The normal type of patients arrive with a probability of 0.6. The emergency type of patients arrive with probability of 0.1. And as you can see, if there's more than 1 patient come to our emergency type of doctor, the second patient will be directed to another hospital. And then for all the patients that are inside our hospital right now, each specialist sessions will take about 40 minutes. And even if that specialist has finished the treatment for the previous patient, he or she has to wait until the next patient's appointment, which is in 40 minutes. And treating normal type of patients takes about 21 plus 20 times R&D minutes. 60% of emergency type of patients takes 30 plus 30 times R&D minutes to leave the clinic. 40% of emergency type of patients takes 120 minutes to leave the clinic for the operations. At the time of 5 o'clock, all the other types of doctors will go home and leave work, except for our emergency type of doctor, who has to stay at the hospital for 24/7. At this time, if there are more than 1 emergency type of patients arrive, similarly, the second patient will be directed to another hospital.
Let's move on to the model in Sigma. Since there is a limit on the number of variables can be used in the software, we divided the model into 2 sets of simulations to meet our goal. Variables written on the left are common variables we used in both models, and for each of them, we have a few unique variables. Model 1 traces the average number of patients in the system and number of emergency patients booked in a day. Model 2 traces the waiting time for each patient in special and regular queues separately in the system. This is a hand-drawn simulation diagram of our model. State changes written in black represents the common variables and changes in both Model 1 and 2. Blue represents the unique state changes in Model 1, and red represents Model 2. In order to visualize the simulation process, we have also uploaded a video recording how the model actually works. Taking Model 1 as an example, at time 0, the simulation starts with all values set to 0. Event check represents check-in table, which signals which department the patient needs to go. It self-generates with a delay that follows an exponential distribution. At event space 1, space 2, and emergency arrival, special queue, regular queue, and emergency queue all increment by 1 each time. If any of the doctor is idle, begin service of that particular type is scheduled, and the status of the doctor is set to be busy. Event D1, D2, D3, and D4 all represent the completion of the treatments or operation. In a delay of 540 minutes, event close is scheduled. All offices except emergency room stop service, and queues are emptied. Anyone comes to the hospital without seeking for urgent care is balked. Any patient in the emergency queue when the emergency room is busy is balked as well, which is recorded in event balk.
Met with 3 modeling difficulties in our model. The first is the closing condition. In our model, appointment and normal doctors work 9 hours per day, but emergency doctors work 24 hours every day, and it's somehow complicated to show this feature. Next is the variable outflow. We actually have too many variables in our model, but Sigma only allows a maximum of 15 variables to be added in without a developer's license. Therefore, we have to do the tracing in similar separate models. The third problem is the normal doctor assigning. In our design, we have a normal doctor and an assistant doctor. The normal doctor has higher priority than assistant doctor, and we have to show this feature. So, now comes to the results and conclusion. In the simulation output analysis, we do the chi-square goodness of fit test to test the uniformity and the sign test to test the dependency to make sure that our model is reliable. Moreover, we use the replication method and make 15 independently seeded runs with 10 steady state observations per run. To avoid bias, initial transient has been removed from each run, and the 95% confidence interval is calculated to get more accurate data. We find that the average number of patients in the system is approximately 5.427 people per day, and if we only count the working hours, then N is nearly 12 people. In addition, before we warm up the system, the average number of patients get booked is 10.4 every day, and after the system get warmed up, this figure increases to 10.8. We also traced the waiting time of patients coming to the specialist and the normal doctors. According to our calculation, the average time one waits for the specialist is nearly 272.29 minutes, and the average time one waits for a normal doctor is nearly 184.33 minutes. Results are shown in the graph, and we find that the number of patients in the system grows kind of quickly, which means that both the queue and the waiting time gets longer. Therefore, we conclude that we need to increase the doctors in our hospital so that patients can receive treatments on time.
Now comes to the possible sources of error. Firstly, during our analysis process, we assumed that the number of patients arrived followed the exponential distribution. This may not be the optimal simulations of the real-world situation. Also, we estimated the average hours for normal cases and emergency cases, when in the real life, the time each doctor needs might be different. The next is the variance and event limits due to the limitation of the variables in a Sigma model. And also, since we only run a small interval of time, there may exist some initial bias. Therefore, we use a method of replications to reduce the bias. Thank you for watching our video, but we are not looking forward to seeing you in our hospital because you will balk with an extremely high possibility.